Good morning, everybody. Let's get started with the class for the day. And last time, what I have done is I have talked about Central Limit Theorem. All right. So just to recap, the Central Limit Theorem, also we talked about sampling distribution, of course, that goes with Central Limit Theorem. Now, the Central Limit Theorem has two conclusions. The first conclusion is that mu sub x bar is the same as mu, and the second conclusion is that sigma sub x bar is the same as sigma divided by the square root of the sample size. So these are the two conclusions of the Central Limit Theorem, and these conclusions hold true when your sample size n is greater than or equal to 30. It holds true regardless if your sample size is greater than or equal to 30. However, if your sample size is less than 30, it still holds true if your initial population is normally distributed. The population from where you are sampling, okay? Population from where you are collecting data or sampling, if it is bell-shaped or normal distribution or Gaussian distribution, then it is, these two conclusions are going to hold true. Okay, next, we also talked about, of course, sampling distribution, which led us to the conclusions of Central Limit Theorem. Hold on one second. I'm gonna have to mute people. All right. If you want to speak, please unmute yourself and talk. All right. Because of the background noise, I muted everybody. Now, what is a sampling distribution? We talked about it. Sampling distribution is the distribution of sample means, okay? Sampling distribution is the distribution of sample means. So I gave you a very simple example here. Look, if you have a population with only 100 items in it, and you collect samples of size 30, how many such samples can you collect? This many. Okay. How many different such samples can you collect from a population that has only 100 items in it, and your sample size is 30? These many different groups of 30s are possible. And for each of them, there will be one, average. Now, if you take all of these possible samples and find the averages and graph them, that is going to be your sampling distribution. And in this case, it's going to look like this. And this is not the distribution of the population, but rather the distribution of the sample means or sample averages for all of these samples. And this distribution also has a mean, and we call this mu sub x bar. This distribution has a mean, we call it mu sub x bar. And this distribution also has a standard deviation, we call it sigma sub x bar. Now this mu sub x bar and sigma sub x bar has a relation to the original population or with the original population, okay? And that relation is this, which are the conclusions of the Central Limit Theorem. Mu sub x bar, this average is the same as the average of the population, which is mu. Number two conclusion, this standard deviation sigma sub x bar is the same as the standard deviation of the population divided by the square root of the sample size. In our case here, we considered our sample size n to be 30. It could be any number, right? Any number greater than 1, integer I meant. So these are the two conclusions of Central Limit Theorem, or CLT. Again, just to emphasize, these conclusions hold true always when n is greater than or equal to 30. But if n is less than 30, then the initial population from which you created the samples, initial population from which you created the sampling distribution, right? If that has the normal distribution, then these two conclusions are gonna work even if your sample size is less than 30. So that's what, in short, sampling distribution and central limit theorem. Any question, anybody, on these two topics, sampling distribution and central limit theorem? We talked about it in details last time, and you had a little bit of time to absorb it. We have solved a few problems using the central limit theorem concepts. So if you looked at the example problem that I did, and if you looked at the class notes and listen to the lecture, you should be in a good position to get a good understanding of the sampling distribution and central limit theorem. However, if you're still shaky on these two topics, let me go ahead and continue and do more problems, which I will do today. And along the process, ask me questions to make sure that you clarify your questions, things that you do not understand. Okay? If you don't follow along anything, just ask me. I'll be happy to explain. All right. Having said that, let's move on. So next, we have done this problem in the class last time. Is this problem okay, everybody? Did you guys get the problem? Any question, anybody? Any difficulties? No question? Even though you don't have any question, I do. I'm gonna go ahead and do the exact similar problem here. This second one, the one I expected you to look at home, is very much like the last problem, the one I solved here, right above. But this one I did not solve, and I just changed the numbers a little bit. I haven't made any changes other than just changing the numbers. So I just want you to walk through the steps progressively and get a feel for it. All right? Okay. Now, Mr. Zach, the founder of Facebook, recently announced that an average person spends about 60 minutes per day on social media. Assume that the time spent on the social networks is normally distributed with standard deviation 30 minutes. All right. Time spent on this is normally distributed with standard deviation 30 minutes. So key observation. So here, pay attention to this normally distributed, okay? Standard deviation 30, mean 60. So these numbers you may want to pay closer attention to. Now let me walk through this problem, and along the process, I will be using just regular normal distribution, then I will be using sampling distribution and the central limit theorem, okay? I'll be using sampling distribution and the central limit theorem. If you take a sample of 25 people who use the social media, then what is the average of the sampling distribution with sample size 25? So actually, I just didn't do the regular one. I just jumped into the sampling distribution here. So instead of selecting randomly one person, you selected 25 people from the population. Okay. That comes from where? That comes from a sampling distribution of sample size n is equal to 25. So from the original population, you keep taking samples of size 25, 25, 25, many, many times. And you find average for each of these samples. And if you graph it, it's kind of supposed to look like a bell-shaped curve. All right? It's supposed to look like a bell-shaped curve. All right? Now, I want you guys to tell me. So everybody, please participate. The objective of this problem is not that I'm going to show you how to do it, because I already have done so. The objective of this problem is that you be interactive and you try this problem and try to solve it along with me. Okay, I'm going to guide you through the process. All right, so what is the average of this sampling distribution with sample size 25? Can you please help me? What is the
60?
It's what? I'm sorry?
60?
Exactly. Thank you, Araceli. 60. You're right. It is 60, but could you explain why it is 60?
Since the sample size is 25, and then if we look at the number before the standard deviation, well, that's how I got my answer, because it's 60. And then in the previous problem from last class, we also had a similar one. So we used the mean.
Yes.
Yeah.
What you're trying to say is this, in more of a teacher's language, you're trying to say that mu sub x bar is equal to mu. That means mean of the sampling distribution with sample size 25 is which is this, right? Mu sub x bar is the same as the mean of the population, original population. So that's what you're trying to say. So I get it, and you're correct. However, I kind of still would like to ask you one more question, Araceli, which is this. The sample size here is 25, but remember our central limit theorem tells that this is true only if your sample size is greater than or equal to 30. How come even though this is less than 30, we could still use this? Can you clarify that?
Because it's a bell-shaped curve.
Yes, because original population is what? Normally distributed. I said that in the problem. If I were not to say this thing, so let's say this was not there, this statement, normally distributed. In that case, you could not use this. You could not say that mean mu sub x bar is equal to mu is equal to 60. You could not say that because it is not guaranteed to be true unless the sample size is greater than or equal to 30. Unless the sample size is greater than or equal to 30, it is not guaranteed to follow that rule. However, we did say here that it is normally distributed, therefore it is gonna hold true, even though the sample size is 25. Is this clear to everybody?
Yes.
Yes.
Okay.
Yes.
Next, thank you. Next, what is the standard deviation? What is the standard deviation of the sampling distribution with sample size 25? Now that you answered the last one, this one you probably would be feeling comfortable as well. What I'm asking, what is sigma sub x bar? In the last question, I asked you what is mu sub x bar. In this question, I'm asking what is sigma sub x bar. So can you tell me what is sigma sub x bar?
Six.
6. Is that somebody said 6?
Yes, 6.
How do you get that number?
Because sigma is equal to sigma of or sigma x bar is equal to sigma over the square root of the sample size. So I took 30
Perfect.
divided by square root of 25.
Perfect. So 30 square root of 25 is 5, which is going to give you 6. So sigma sub x bar is equal to 6, and mu sub x bar was 60. Great. Find the probability that a randomly selected person spends more than 120 minutes on the social media. So this is so read carefully. A randomly selected person is just one person. So we are not talking about sampling distribution anymore. We are talking about the regular population. We are not talking about the sampling distribution. We are talking about the regular population. All right. So now, how do you find that? This one is easy. So let's clean up the screen. A randomly selected person spends more than 120. So mean is 60. 120 is somewhere here, right? More than 120, meaning you are looking for this. So you're looking for probability of x is greater than or equal to 120. Probability of x is greater than or equal to 120. Now this is something you already have seen. We have to convert it into standard normal distribution, which has a mean of 0 and standard deviation of 1. So this 120 is going to map to something here, z value, right? We are looking for this z, and z is equal to x minus mu over sigma. In this case, x is the point in question, which is 120, minus mu is 60, divided by sigma is 30. Okay, so this is also given in the problem, 30. So that's going to give you just 2, because 120 minus 60 is 60. 60 divided by 30 is 2. So z is 2. So we are looking for this area. So probability of x greater than or equal to 120 is the same as the probability of z greater than or equal to 2. However, you know that normal distribution does not give you, standard normal distribution table, it does not give you area to the right, it gives you area to the left. So to find that, we just take the complement of it. 1 minus probability of z less than or equal to 2. Now, if you look it up in the table, you should get some value. So can somebody tell me what the value is for z is equal to 2? Somebody please look it up in the
0.9772.
0.9772.
72.
Thank you. That is correct. 0.9772. All right. So that's going to be what? 1 minus 0.9772 is 0.2022. Okay, so that's what it is, which is about 2.22%. So that's the probability that a randomly selected person would spend more than 120 minutes on the social media. Of course, the next question you can guess probably already, which is find the probability that 25 randomly selected persons spend more than 66 minutes on the social media. So let's go ahead and do the problem. So you know what, I'm gonna do these problems, even though it's not on the lecture note, I'm gonna do this one. This is for one person, right? Now I'm gonna ask you to do the same thing for 25 people. So n is equal to 25. I want you to find the probability that average of 25 people's social media time would be greater than 120. Okay, greater than, this one was for one person, right? Now I'm talking about the average of 25 people. So what symbol should I be using here? I used X over there because it was one person. Now I'm talking about 25 people. What should I be using? For 25 people, X does not make sense, correct? It has to be what? X bar, the average of 25 people. So I'd be putting X bar greater than 120. So this is a point that you need to be clear about. So average of 25 people, that's why we are using X bar. Here we use only X because we are talking about only one person. So I kind of want to find out what is the average of 120, average of 25 people. What is the probability of the average of 25 people being greater than 120, right? So which, by the way, is going to be probability of, now we are not going to use Z anymore, which we did here. We are going to use Z sub X bar greater than or equal to some value. Now we are going to have to find that value. So here is the interesting part of this. Mu still doesn't change, which is 60. In this case, sigma was 30. Here, sigma sub X bar is actually 6, which we just found. So this is going to be narrower compared to this one. So I'm doing it side by side so that you can follow along. Now we are going to have to go to this guy, mean 0, standard deviation 1. Now 120 is going to be somewhere here, right? So we are looking for the probability that average of 120 people, average of 25 people is greater than 120. Now this 120 is going to translate to a point right here. We do not call it Z like we did here. We are going to call it Z sub X bar, just to identify that we are dealing with sampling distribution, G sub X bar. All right. Now, look, how do you go there? Z sub X bar is equal to mu sub X, sorry, not mu sub, X bar minus mu sub X bar over sigma sub X bar. All right. X bar is the point in question, which is 120. So it's going to be 120 minus mu sub X bar is 60 divided by sigma sub x bar, which is 6, right? Sigma sub x bar 6. Now, if you do the math, is 60 over 6, which is 10. So z sub x bar is 10. That's a huge g sub x bar. So this is the same as saying, so look here, probability that x bar is greater than or equal to 120 is the same as probability of z sub x bar being greater than or equal to 10 standard deviations out there. That's extremely unlikely. So which is 1 minus probability of z sub x bar being less than or equal to 10. Now the standard normal distribution table just goes up to 3.5 standard deviations. And you can imagine 10 standard deviations, that's way out there, all right? You can imagine that 10 standard deviations is way out there. The table even does not cover. So this is gonna be 1 minus something like 0.99999. Put 5, 6 nines. So that's gonna give you 0.000. 1, 2, 3, 4, 5, 6, 6, 1. Compare this number and this number. The reason I did this part of the problem, even though it's not in the problem, is because I wanted to compare it. See, if you're talking about one person, the chances of that person spending more than 120 minutes is about 2%. It's small, yet not that small. Yet it's something that could happen. However, when we just move it to average of 25 people, then this number is less likely to fluctuate. Meaning that the chances that 25 people, their average social media time will be more than 120 is extremely small. That probably wouldn't happen. Very unlikely. So that's what it is. You can see how the sampling distribution reduces the standard deviation. That means restrict your data points around the mean, squeezes the data points around the mean strongly. Whereas for the regular distribution, it's kind of like less compact around the mean. And that's why as you increase this sample size, okay, as you increase this sample size, what's going to happen? This standard deviation is going to go down even further. So let's say if I make my sample size n is equal to 100, now what is the new sigma sub x bar going to be? Sigma sub x bar is going to be sigma over square root of the sample size, right? Sigma is 30 divided by square root of 100, which is 30 over square root of 100 is 10, 3. Do you see? If you increase the sample size to 100 from 25, your standard deviation is going to cut into half. Meaning from 6, it goes down to 3, which should make sense to you, which should make common sense, because what happens is that as you increase your sample size, your numbers become more reliable. Okay, that means you don't go too far from the mean. So for sample size of 100 is probably going to be more like this, more compact towards the mean. Any question, anybody so far? Anything that I could answer?
No.
All right. Now, let's go ahead and bring the next question. Find the probability that 25 randomly selected persons spend more than 66 minutes on the social media, which is easy. This time n is equal to 25. And we are trying to find out the probability that x bar is greater than 66, which is pretty easy. We know that for sample size n is equal to 25, or sigma is 6 and mean is 60. We're going to go into standard normal distribution for the sampling distribution, 0 and 1. Probability of z sub x bar is greater than something. So this is 66 right here. So we are looking for this, right? So this is going to translate to a point right here. And we are going to be looking for this. This is going to be my z sub x bar, which you can see, by the way, z sub x bar is equal to x bar minus mu sub x bar over sigma sub x bar, which is going to be x bar is 66. So that's your x bar minus mu sub x bar, which is this mu sub x bar, which is 60, divided by sigma sub x bar, which is this 6, and that is 1. So z is 1. So probability that average of 25 people is greater than 66 is the same as z sub x bar greater than 1. Now that is the same as 1 minus the probability of z sub x bar is less than 1. One minus the probability of g sub x bar is less than 1, and you can find it, which is going to be 1 minus 0.1587. So 0.1587, 0.8413. Oh, did I make a mistake? I did make a quick mistake, so let's fix it. This is 0.8413. This value for z is equal to 0.8413, which is going to give you 0.1587 or 15.87% chance that average of 25 people would be greater than 66 minutes, which is like going 1 standard deviation to the right. See, this is z is 1. So if you go to 66, you go 1 standard deviation to the right. If you go 1 standard deviation to the right, 1 standard deviation to the left, you include 68%, right? And outside should be roughly about 32%. Half of 32 is 15.87 roughly. It's not exactly 68, it's a little more than 68. And that's what it is. Now you should be very comfortable, very used to by now how to find these probabilities. I know it's not easy. When you are looking at it the first time around, it's not easy, but just don't give up, okay? Don't give up and keep working. You'll get there. Now let's see if I put anything else here. Okay, so the next one is find the probability that a randomly selected person spends between 60 and 90 minutes. Okay, and this one is very easy. I did it before, but I'll do it again. A randomly selected person spends between 60 and 90 minutes. Is it 60 and 90? 30 and 90. So this is your 60, standard deviation 30. This is 90 and this is 30. So we are looking for the probability that a randomly selected person, so we will use X, not X bar. We use X bar only when we are dealing with sampling distribution, which, by the way, you can figure it out. I'm not gonna spend time doing it again. I have done it many, many times. This will be -1 and this will be +1, because 30 is gonna be 30 minus 60 over 30, which is -1, and 90 is gonna be 90 minus 60 over 30, which is 1. All right. And we are looking for this area. So probability that a randomly selected person spends between 30 and 90 minutes is the same as Z falls between -1 and +1. Z falls between -1 and +1, which, by the way, is the same as probability of Z less than 1 minus the probability of Z less than -1, and that is going to be 0.8713, 0.8713 minus 0.8413, I think. Is it 84? 0.8413, sorry, not 87, 8413. So if you subtract this, it should be 68 point something, 228 or something. 0.8413 minus 0.1587, which is 68.26, 0.6826, which is the same as 68.26%. So the probability that a randomly selected person spends between 30 and 90 minutes is like going between 1 standard deviations in either direction. So you move 1 standard deviation to the left from 60 to 30, right? 60 minus 30 is 30. You moved 1 standard deviation to the left, and also you'll be moving 1 standard deviation to the right. 60 plus 30, which is 90. And you know, if you move 1 standard deviation from the mean to the right and 1 standard deviation from the mean to the left, you include roughly about 68.26% of the data. So that's what you found here. This is, keep in mind, this is for sample size of 1, meaning we are talking about population. In the next problem, however, it is asking you to find the probability that the average, so now we are dealing with sampling distribution, the average of 25 people falls between 54 and 66. So now this. In between, you will not be using X anymore. You're going to be using X bar. Why X bar? Because we are dealing with sampling distribution. Now that is going to be equal to probability of Z sub X bar between -1 and +1. Now let me just draw the quick diagram here. This is your sampling distribution with sample size n is equal to 25, and this is your mu sub X bar is equal to 60, and sigma sub X bar is equal to 6. Now we are going to translate this or map this into Z sub X bar 0 and 1, and 54 is here and 66 is here, and we are looking for this middle area. Now what does 54 translate to? So it's going to be 54 minus 60 divided by 6, you can get -1. That is going to be -1. And what is 66 going to translate to? 66 minus 60 divided by 6, which is 1. It's exactly like this problem. So it's gonna be between this and this, which is probability of z sub x bar is less than 1 minus the probability of z sub x bar less than -1, which is probability of z sub x bar less than 1, meaning, again, the same thing, 0.8413 minus 0.1587, which is going to be 0.6826, which is 68.26%. See, compare this side by side. For one person, the variation could be a lot higher for the same probability, 68.2%. For one person's amount of time spent on social media could fluctuate a lot. And that's why you see this variation. Whereas for 25 people, their average cannot fluctuate as much from the mean. See, for 25 people, going between 54 and 66 is like for one person going between 30 and 90. You can see how much spread out it is. And that is because of the standard deviation. Standard deviation is higher for one person, but standard deviation is lower for 25 people. And that is the moral of the story of this problem. Any question, anybody, before I move on? Anyone? Is it getting too hard? Are you being able to handle it?
I get it. It's just more steps. So I think I just need to memorize a little more and maybe do some more problems on my own.
Okay. Okay. Yeah, it is true. And by the way, just to make you feel at ease, this is the hardest part of the semester. I think we are done almost. It's not gonna get any harder. The last thing that we talked about was a bit harder was the Bayes theorem. So that's one topic I consider to be a little bit advanced. And central limit theorem, I consider it to be a little bit advanced. I don't know. Honestly, I don't even know if all the teachers for this class covered this topic, the central limit theorem. I do. Maybe they do. I don't know. But Bayes theorem, I think I might be the only one who is covering it. I'm trying to do a little extra for you. Central limit theorem, they probably cover, but I'm not sure to what depth. Okay. I could have just told you that, you know, the conclusions of the central limit theorem are mu sub x bar is equal to mu and sigma sub x bar is equal to sigma over square root of n. And I could just use these results. That's okay. But I kind of feel that I needed to give you more in-depth analysis of how this thing comes about into play so that you can get a more solid understanding of the topic. So that's why I'm kind of going over these things a lot more. And Bayes theorem, by the way, it is not technically, I don't think it is even part of the syllabus, but I kind of want you to do Bayes theorem because this has something to do with conditional probability. And in today's world, conditional probability is everywhere. Like even right now, we are dealing with all over the globe, the conditional probability. So you could think of probability of developing COVID-19, okay, or coronavirus, given that you have flu, cough, or fever, cough, or pain, body aches. Do you see? This is actually conditional probability. Given, so you can do an analysis of pandemic or epidemic, whatever is out there, you know, using mathematics, you can model it. Given that this sample, what is the probability that someone will develop COVID-19. Okay, so that's what it is. Okay, and this is nothing but Bayes theorem, by the way. This is nothing but Bayes theorem. All right. One last question that I kind of want to do here, which is this. The nicotine in cigarette. All right. I did the problem here. I'll go over this, and that will be the last topic from the central limit theorem and sampling distribution. The average amount of nicotine in a cigarette is about 12 milligrams. But for your information, when you smoke a cigarette, you only consume 0.95 milligrams or so. So on the average, there are about 12 milligrams, but in a cigarette. When you smoke it, you actually consume roughly about 1 milligram, not the whole 12 milligrams. We assume that nicotine distribution, that doesn't mean cigarette is good, by the way. I don't know. I never smoked in my entire life, a cigarette even. So in California, I think people are a lot more health conscious. So I don't see many people smoking, but in other states, when I go, my goodness, people smoke like chimney sometimes. It's crazy. Everywhere, people are smoking on the street, walking around, smoking on the sidewalk, sitting down and smoking. I have been to a couple of other states where I have seen that. Hopefully that number has gone down. Anyway, so we assume that nicotine distribution in cigarettes is normal. So key information. It's normal with a standard deviation of 1.5 milligrams. We assume that the distribution of nicotine in the cigarette is bell-shaped or normal or Gaussian with standard deviation 1.5 milligrams, and the average mu is 12 milligram. A cigarette manufacturer claims that it has reduced the amount of nicotine in its cigarette. You, the curious cat, actually go out and take a random sample of 50 cigarettes. You find that the average is 11.8 milligram as opposed to 12 milligrams. Do you believe that the cigarette manufacturer is telling the truth? Assume that you will believe the manufacturer if there is less than 5% chance of the average being less than given average. So this problem is a little bit hard to understand. It's not because, well, maybe it's the concept as well as the wording, both. I couldn't find much better way of expressing it. I just did as much as I could. Hopefully it makes sense. I'm gonna try to explain it. Let's say cigarette manufacturers didn't do anything. They really haven't changed anything. All right? They're just saying that, oh, okay, we reduced it. In that case, what are the chances that if you took a random sample of 50 cigarettes and you'll be finding 11.8 milligrams average, given that the population average is 12. And if that chance falls below 5%, then we'll say, okay, there is a 5% chance that cigarette manufacturers are not telling the truth, but 95% chance that they are telling the truth. So if from our calculation, if we find the probability of X bar being less than 11.8 is less than or equal to 0.05, then we will say the cigarette manufacturers are telling the truth probably. Whereas if it is greater than 0.05, probability of X bar greater than 11.8, that probability, if it is greater than 5%, we will say that maybe we will question the manufacturer's claim. we will question the manufacturer's claim. That's what it is. Once again, if the manufacturer hasn't done anything, you could get 11.8 milligrams average for 50. On the other hand, if they did something, they actually made some changes that lowered the amount of nicotine. In that case also you could get 11.8. So the question is, which one would you accept, or under what circumstances would you accept it? If they didn't do anything, you could get 11.8. So did they do it or they didn't do it? You don't know. On the other hand, even if they did it, in that case you could get this. So it depends on what the probability is. All right, so let's go ahead and do the problem. A few things. Mu is equal to mu sub x bar is equal to 50. Oops, not 50, sorry. 12. Why? Because my n is equal to 50, which is greater than or equal to 30. So it does not matter whether the initial population is bell-shaped or not. We would still be able to use the conclusions of the central limit theorem. And sigma sub x bar is equal to sigma over square root of n. Sigma is given to be 1.5 divided by square root of 50. All right, square root of 50. And that number comes out to be, by the way, let's see, 1.5 divided by 50 square root is 0.0707. 0.0707. So to find the probability, this should be x bar. Probability of x bar greater than 11.8 is the same as 1 minus the probability of x bar being less than 11.8. Now 11.8, so remember, this is what you had, 12 here, okay? And sigma sub x bar is equal to 0.0707. 11.8 is going to be somewhere here. Greater than meaning we are looking for this area. Okay. Something. Oh, that's why there is a typo in this problem. It didn't make sense to me. Okay, hold on. Let me fix it. What we are looking for is this. Probability of x bar less than 11.8. Okay, less than 11.8. We are not looking for greater than. What are the chances that is going to be less than? So we are, in essence, actually, let me just do a little bit of erasing. We are looking for this area, not the other area. That means if they haven't done anything, if they haven't done a single thing, what are the chances that is going to be less than or equal to 11.8? So that's what we are trying to find. And for 11.8, this problem has too many typos. I don't like it. I need to fix it. Sorry about that. Do you see that this number should be negative? Because 11.8 minus 12. So please, my apology, everybody. Ignore these calculations, okay? Even this one. I'm just gonna do it for you. All right, just let me do it clearly here. This is 12, and let's say 11.8 is here. We are looking for probability. This is wrong. Probability of X bar being less than or equal to 11.8. That's what we are looking for. Now, this calculation is actually right except for the sign. This should be negative. 11.8 minus 12 is negative 0.2 divided by 1.5 over square root of 50. So that is going to be 0.2 divided by 0.0707. So there's going to be, all right, so 0.2 times square root of 50 divided by 1.5. Okay, perfect. It comes out to be probability of Z sub X bar being less than or equal to negative 0.94. This is positive, but it should be negative. Other than that, this calculation is right. But this one, just ignore it completely. So probability of X bar less than or equal to 11.8 is the same as the probability of Z sub X bar is less than or equal to negative 0.94. So in the standard normal distribution, this is 0, this is 1, and negative 0.94 is here. So we are looking for this area. All right. So which is gonna be, now can somebody tell me what this value is for negative 0.94? Please look it up. I think it is gonna be this number, but oops. I think it's gonna be this number, 0.1736, but can you verify that please for me? Has anybody found 0.1736 or you got something different?
It's 0.1736.
It is 0.1736?
Yes.
Okay, good, thank you. Which is the same as saying 17.36% chance. So the moral of the story is this: even if the manufacturer did not do anything, okay, even if they did not make any changes to reduce the amount of nicotine in the cigarette, there is still about 17.5% chance that you will get less than 11.8 milligrams. Our standard was that if it is less than, if that probability, this probability is less than 5%, then you would assume that, oh, manufacturers are probably telling the truth. There is a 5% chance that by mistake, by randomness, we got that number, but there is a 95% chance that they told the truth. But here, there is 17.5% chance roughly that they didn't make any changes, and by random luck, we got lower amount in the average. So we'd probably say maybe it's more likely they haven't told the truth. Is it okay, everybody? This problem is exactly the same problem. Instead of average amount being 11.8, I changed it to 11.7. So I'll go ahead and do it for you since we had a little bit of typo issue in the last problem. So again, everything is the same. So we are looking for probability of X bar being less than or equal to 11.7, given that they haven't done anything. All right. So mu is 12, and that's mu sub x bar, which is equal to mu, and sigma sub x bar is equal to sigma over square root of n, which is sigma is 1.5 divided by square root of 50, because we are considering a sample size of 50, that is 0.70, sorry, not 0.70, 0.0707, I think, 0.0707. So your sigma sub x bar is equal to 0.0707. Your sigma sub x bar is 0.0707. Now we need to translate this into standard normal distribution, which is mean of 0, standard deviation of 1, and our 11.7, we want to find 11.7 less than, meaning right here. So what does 11.7 translate to? We need to find that. So z sub x bar is equal to x bar minus mu sub x bar divided by sigma sub x bar. So z sub x bar is equal to x bar is the point in question, which is this guy, 11.7 minus mu sub x bar is 12. All of it divided by sigma sub x bar, which is 0.0707. And let me do the calculation here. It's going to be negative 0.3 divided by 0.0707. Okay. Did I do it right? Okay. 11.7 minus 12 is negative 0.3 divided by sigma x bar, which is 0.0707, which is negative z sub x bar is equal to negative 4.24. Can you please do the calculation with me as well while I'm doing it? Just to make sure that I get this right. Okay. All right. So this comes out to be negative 4.24. So this is negative 4.24. I just realized that I just made another mistake. Sorry about that. I'm making too many mistakes in calculations today because I'm doing it as I am teaching. That's why. So I just realized that I made a mistake in the other problem and I will fix it. So this x bar is less than 11.7. So probability of z sub x bar is less than or equal to negative 4.24, negative 4.24. All right. Now, if you look it up in the table actually goes only to negative 3.5. Okay, if you look it up, you'll see. And that for associated with probability of z less than or equal to negative 3.5 is roughly about 0.0001. So this is even smaller. So it's going to be even smaller. So it's going to be probably 0.000, maybe another 0.1, which is what? 0.0001%. Okay. So 0.00001 divided by, okay, so not divided, times 100. So this should be this 0.001%. So 0.001%. Okay. So there is a 0.001% chance that by randomness, by random luck, you will get 11.7. So the conclusion here is that it is much less than 5%. It's much, much less than 0.05. Therefore, the manufacturers are probably telling the truth. Okay? Manufacturers are telling the truth that they have reduced the amount of nicotine in the cigarette. Now, let me go back to the last problem. And this problem, I promise I'll fix this one. Just ignore the entire thing. There is too many typos. I just realized that this calculation is also wrong. So let me use red for this. Z sub x bar is equal to x bar minus mu sub x bar divided by sigma sub x bar. All right. X bar is the point in question. In our case, it was 11.8. 11.8 minus 12 divided by sigma sub x bar, by the way, was 0.0707, which is going to give you z sub x bar is equal to negative 0.2. 11.8 minus 12 is negative 0.2 divided by 0.0707. So negative 0.2 divided by 0.0707, which is actually negative 2.8, I'd say 3. So probability of x bar less than 11.8 is the same as the probability of z sub x bar less than negative 2.83. This number is not right. Okay, so I did it for 94.94. That's how I got this. So now, can somebody please look it up in the table for negative 2.83? What do you get for probability? There's going to be the actual answer. Could you please look it up? I want everybody to try it. Okay, 2.83. For 2.83, yeah.
0.0023.
0.0023. That sounds about right. Could somebody else verify that, please?
It is.
It is? Okay. So, which is much less than 0.05, right? Which is much less than 0.05. So, there is less than 5% chance that you will get it randomly. So, therefore, our conclusion is that cigarette manufacturer is probably telling the truth. They have reduced the amount of nicotine. All right. And what I'm going to do, I don't like this problem. This thing, there are too many typos. Initially, I meant to do the problem for one number and then I changed it and forgot to change the solution. That's what has happened here. I'm going to update these values and I'll resend it to you. Okay. Any question about these two problems with the same numbers almost, except for one number being different? Are you guys following it? Everybody okay with it?
Yes.
Okay. Any question, anybody? All right. If not, we are going to move on to the next topic. This is pretty much the last, it's kind of like the second half of the semester. We have, this is, about the second half of the semester. So this stuff that I'm going to cover from now on, these are very useful in the real world. It's confidence interval, hypothesis testing, regression analysis, correlation, all those things. These are very important, but topics are easier. It's not hard, Now that we have been through the peak of difficulty, which is Central Limit Theorem as well as the Bayes Theorem, we are in a good condition or good position right now. Everything else from now should be easier. So I'm just gonna go ahead and get started with this thing, and then I'll try to cover as much as I can today, and then we'll finish. You have the weekend. Please go over the materials over the weekend, and then I will also put a new homework online. And if you would please go over those homework and ask me questions if you have any, I'd be happy to answer. All right. So the next topic is going to be about confidence interval. Before I give you the academic definition of everything, I'm just going to give you a very simple example, something that you can relate to. That way you will get the true understanding of the topic. So let's say I ask you to find the number of hours the students at Hartnell College study per week. Okay? If I ask you the question, sorry, I think I received a phone call somehow. So let's say you want to find out the number of hours the students at Hartnell College study per week. So what do? You go out and survey, let's say 100 people, okay? You survey 100 people and find that the average number of hours that they study is, let's say, 17 hours per week. They study 17 hours per week on the average. So how did you get that number? By surveying 100 students. Now, obviously, this is not the exact number for the entire Hartnell College students, right? The average number of hours the students at Hartnell College study is not exactly 17, probably, because the Hartnell College has 15,000 students. You really didn't go out and ask 15,000 students, hey, how many hours do you study, and got 15,000 numbers and added them divided by 15,000. No, you haven't done it. What you have done, you asked about 100 people and you got 17 as your answer. Now, if I were to ask you the question, so this is the critical question. If I were to ask you, how good you feel, how confident are you in this number? Okay, if I were to ask you, how confident are you in this number, the 17 that you got, you might say, I am 80%, 90% confident that actual average is going to be somewhere around 17. So if you were to put a number, you could say, I found 17, right? I found 17 X bar, sample average, but with good common sense and my experience, I could say it could be as low as 16 or as high as 18. And very likely that the average number of hours students at Hartnell College study per week is going to fall between 16 and 18 hours based off of my calculation. How confident are you? I am 90% confident. Okay, that means 90% chance, 90% likelihood that, okay, your interval actually contains that true average number of hours that Hartnell College students study. And what I just told you with this example is exactly what confidence interval is all about. Okay, this is exactly what confidence interval is all about. You do a calculation, you find a sample, you collect data, and you do something, okay? And then you go ahead and kind of create an interval around that number and you say that, you know, you associate some level of confidence with that interval, okay, then probably you'll say I'm 90% confident. On the other hand, so one student did 100, another student did 2, let's say, for the sake of argument, and that student found 20 hours. The average of 2 students that he asked is 20 hours. Who do you think would be more confident in the calculation? So this student says that, okay, it could be as low as, let's say, 18 or as high as 22. Which student would have more confidence in the calculation? Is it student 1 or student 2? What do you think?
Student 1.
Yes, of course. Because why? Tell me why.
Because he did a larger sample.
Exactly. Good. Because he did a larger sample, right? And now I kind of want to ask you another question. Let's see, Mijen, see if you can answer this. Why do you think that this student is going to, intuitively, yes, you're right. Why do you think that this student is going to have bigger confidence compared to this student? Or greater confidence compared to the second student? Why? Intuitively, it makes sense, right? You have more people, you are going to be more confident. This person took only 2 students and this person took 100 students. So intuitively, it makes sense. This person's calculation is going to be more accurate, meaning that more confidence. This person's calculation is going to be less accurate, meaning less confidence. But can you explain it in any other way other than just the intuition? We have done that, by the way.
Well, mathematically, if you solve it, he would have student 1 has more data points to prove or back up his confidence.
Mm-hmm. Okay, good. Anything else, anybody? Anyone else wants to pitch into the idea? Let me just take the background off. Nobody? Okay, I'll try to explain it. So let's say this is the population distribution. This is the population distribution, meaning sample size n is equal to 1, right? Very simple. When you take sample 100, what happens to this distribution? Does the average change? Does this average change? No, it doesn't. What changes? Standard deviation. Now, for 100 people, standard deviation is going to be 1/10 of the standard deviation. So if this is sigma for this blue one, for this one, sigma is going to be sigma over 10. Why 10? Because square root of 100 is 10. What it does, it squeezes all the data points more closer to the mean. That's why you are less likely to make mistake here compared to here, because this one has lower standard deviation, meaning your distribution is very compact. All right. So that means the data points are going to be mostly clustered around the middle. Whereas in the blue one, it could fluctuate. Blue one could be, if I make my n is equal to 2, then the blue one has a higher standard deviation, meaning that it could fluctuate a lot. This average could fluctuate a lot. Like the way we did for the social media time usage. For one person, the data point can fluctuate a lot. It could go between 30 and 90 very easily. but for average of 25 people, it will not fluctuate as much. And that is why you are getting a better estimate of the mean when you are increasing the sample size, which is, by the way, is saying the central limit theorem. If you increase the sample size, what you are doing, you're decreasing the standard deviation. So that is why it confirms with your common sense. If you take a bigger sample, your conclusion become more accurate. And it does confirm with your common sense. That's what it is. Maijin, did you get the explanation?
Yes.
Everybody else, is it okay? It's a little bit difficult. I don't know how difficult are you finding, but at least for myself, when I learned these topics as a student like you, it wasn't that straightforward. It took me a while to get a good feel for it. As a matter of fact, I didn't get a good feel for these topics until I started to teach and spend a lot more time in my initial years to try to understand and make sense. Nowadays, it comes to me naturally, but it does take a little bit of time to absorb these concepts. So if you don't get it, don't get frustrated. Please be patient. It'll come together. So in confidence interval, what I'm doing, I'm taking a sample. From the sample, I'm either getting mean, proportion, or standard deviation. Okay? And from that sample, I am finding a mean, proportion, and standard deviation. It could be one of these three. And I associate a confidence level with this. I associate a confidence level with this. And it depends on how big my sample size is, basically. So we are inherently using central limit theorem here. Now, we are going to be doing confidence interval for mean. We are going to be doing confidence interval for population proportion. And we are going to do confidence interval for population standard deviation. I take it back. Standard deviation, it just got excluded from the syllabus. So we might not include this, just for mean and proportion. But still, I would give you this example. There are many things that I'm going to be covering in many situations here, like 5-6 different situations. So it's easy to lose track of things. However, many years ago, a student of mine came up with this acronym, and I still thank her to this date. That's a student, I forgot her name. She was taking this class because her family has a history of Alzheimer's disease. So she was trying to do math. She heard that if you do math, you kind of exercise your memory. That way, your chances of getting Alzheimer's disease decreases. So you're less likely to develop Alzheimer's disease if you do math. And apparently, I read articles about it too. So if you do math, that means you're exercising your brain actively. So your chances of developing Alzheimer's disease decreases. So she's the one who taught me this. And before you jump to conclusion, just wait and see what I'm saying. PMS, okay? It is not what you think it is here, all right? She said that this PMS is easy to remember because pretty much everybody knows what is PMS, right? But in this case, PMS stands for something else. P stands for proportion. M stands for mean. And S stands for standard deviation. So she came up with this acronym PMS, proportion, mean, and standard deviation. We are going to do confidence interval. We are going to do confidence interval for proportion, for mean, and standard deviation. Then we are going to do hypothesis testing for proportion, for mean, and for standard deviation. So that's why I thank that student of mine to this date. It helps you remember these things. And in every single session that I have taught since, that student has taught me this acronym, I have been announcing this, by the way. So easy way to remember for hypothesis testing and confidence interval. We are going to do 3 types of confidence intervals. One is for proportion, one is for mean, and one is for standard deviation. Then we are going to do hypothesis testing for 3 things. One is for proportion, one is for mean, one is for standard deviation. So if you remember the PMS acronym, which I believe all of you do almost, then you'll remember how to structure the confidence interval and hypothesis testing along PMS acronym: proportion, mean, and standard deviation. Now let me start talking about things, definitions. Point estimate. What is the objective of statistics? You are not studying statistics for fun, all right? It has a lot of real world application. It's probably one of the most useful topics or subject that has a lot of application in our lives. So it is important, and that's why we are studying. So what is the goal of statistics, basically? You do calculation using sample and make conclusion about population. Let's say if I ask you, what is the average number of years Americans live? Okay, you're not going to collect data from, people who died over the last 10 years or 5 years. Okay, or what is the average number of hours Americans watch TV, which is not the best use of your time, right? What is the average number of hours Americans watch on the screen? You are not going to ask 270 million people and find out what each of them do and then find the average. What do? You take a sample of, let's say, 100 or 1000, and you find the X bar. And that X bar is called point estimate. And from this X bar, what is my objective? I'm not doing it again for fun, trying to find out what's the average number of hours people watch TV. From that sample estimate, which we call point estimate, we try to approximate the population parameter. That means from this sample, we try to find out, okay, on the average in the entire country, how many hours people watch TV, which is, by the way, anybody remember what symbol is that? I'm not going to write it. Population parameter. What is the population parameter for average, population average? At the very beginning of the semester, I talked about it. Then I talked about it in the middle. Now we are coming to the second half of the semester. What do you think? What is the population parameter symbol for population mean? X bar and what is it? Mu. Once again, I'll tell you here, please remember, X bar is the sample mean, mu is the population mean. All of statistics, our goal is basically go from X bar to mu. Using X bar, we try to best approximate mu. Or similarly, using S, sample standard deviation, we try to best approximate population standard deviation. And then sample proportion, P hat. So this is another one, new, I think, but I think I talked about it before. So from sample proportion, we try to approximate the population proportion. So what percentage of the people use iPhone? Okay, you take a random sample of, let's say, 100 people and find out how many of them are using iPhones, some version of iPhones. Then from that, you try to approximate what is the proportion or percentage of people in the US who are using iPhones. So your objective is to go from sample data to population data, or in this case, point estimate to population parameter. All right. So that's what it is. Now, point estimator, it is just the formula that is used to calculate the point estimate. So for X bar, we use this formula. That means you add up all the numbers divided by the total number of data points. For P hat, proportion is the same as percentage. Is the same as percentage. So P hat is X over N. That's the definition for P hat. Again, for standard deviation, you have seen it before. There are two formulas. This is one of them, which is the variance. Square of the standard deviation is variance. So our objective is to find variance for the sample and approximate the variance of the population. That's what it is. An estimator for population median. For median, you could find the sample median, and from the sample median, you could estimate the population median. As you can see, in all of this, what we are doing, we are finding the point estimate. We are doing nothing but finding the point estimate, and from that, we are trying to approximate or get a better sense or understanding of the population parameter. So if you're finding X bar, that means you're finding the sample mean or sample average. From that, you are trying to approximate the population average mu. When you're finding the sample proportion or percentage, from that, you're trying to approximate the population proportion P. If you're finding S squared variance, sample variance, from that, you're trying to approximate population variance. Now, there is one sort of like technical term that I'm going to be talking about shortly, but before that, let me go ahead and define a couple of other things. Parameter space. That's the set of all the values that population parameter can take. One great example is GPA. What are the possible values for GPA? The lowest GPA you can have is 0. The highest GPA you can have is 4, or anything in between, by the way. Anything in between 0 and 4 is also acceptable, right? So your parameter space for GPA is 0 to 4. On the other hand, the number of hours a student studies per day at Hartnell College, it could be as low as 0, or technically or in theory as high as 24. So your parameter space is going to be between 0 and 24, including the boundary points 0 and 24. Similarly, for GPA, the parameter space is 0 to 4, including the boundary points 0 and 4, anything in between. So if I were to sketch it, it's going to be 0, 1, 2, 3, 4. So it's going to be everything. So let's highlight it, what we are talking about. This and everything in between. That's your parameter space. Nothing outside of this. And similarly for this guy. So parameter space is the set of all the possible values that the population parameter can take. For proportion, you can think the number, the parameter space has to be between 0 and 1, because for percentage is restricted between 0% and 100%. Percentage is restricted between 0% and 100%. So for proportion, the parameter space is between 0 and 1. 0% is 0 and 100% is 1. So that's why it's everything between 0 and 100, including, 0 and 1, including the boundary points 0 and 1. Now, once again, we are using estimators, point estimators to be precise. Point estimators. We are using point estimators to approximate or to learn about population parameter. That's basically what we are doing in statistics, right? We are kind of like making conclusion or decisions about the population based on the sample. Now, having said that, there is one technical term I'm going to be introducing. If theta hat is the sample statistic, or in this case, point estimate. If theta hat is the point estimate, remember, a point estimate comes from the sample, okay? Whatever the property or attribute that you're measuring, a point estimate comes from the sample. In general, we represent it by theta hat, okay? So this theta hat, when we are talking about mean, this becomes X bar. This theta hat, when we are talking about population proportion, it becomes P hat. This theta hat, when we are talking about variance, this becomes S square. So this is a generic name for this sample statistics, okay? So if the expected value of theta hat is theta, it is called an unbiased estimator. For example, expected value of the X bar is actually mu. That means all the possible X bars that you can have with that sample size, if they're mean, remember, if their average is mu, then we call it unbiased estimator. Whereas if it is not, we call it biased estimator. So if expected value of theta hat is actually equal to theta, we call it unbiased estimator. Whereas if expected value of theta hat is not equal to theta, we call it biased estimator. Okay, that's what it is. Now, let's look at some of the examples here. Mu, expected value of X bar is mu, which is an unbiased estimator. Expected value of P hat is P, which is an unbiased estimator. Expected value of S square, or standard deviation square, which is variance, is actually sigma square. So this is also an unbiased estimator. However, expected value of S is not the same as sigma. So this is not an unbiased estimator. So you cannot say sample standard deviation is going to be representing population standard deviation in a direct way. It's kind of like unbiased, even though in reality we kind of use it. Okay, so this one is not unbiased estimator. That means you can say it's biased. All right. In reality, however, we kind of do that. Remember, again, statistics, it's a subject. It is not precise mathematics like the way you do 1 + 2 = 3. There is a certain degree of uncertainty or randomness that is inherent in the study of statistics. So some of the things we kind of try to approximate. Like when I make the assumption bell shape, do you think real world is exactly following the bell shape formula or Gaussian formula? No, it doesn't. But what we do is approximately, it's close enough for the purpose of calculation. The real world does not behave like, oh, there is a math formula and I'm gonna follow that. It doesn't work like that. In the real world, it behaves as it is, but as it turns out, we can use mathematics or mathematical models to kind of approximate the real world. All right. If this is the sun, okay, our star, around it, the planet Earth is moving in an elliptical path, right? And all the other planets are moving around the sun in an elliptical path. But we use mathematics to approximately do the calculation. Don't think that the planets are following that mathematics subconsciously and tracing that path. No, as it turns out, the way the natural laws are, it's pretty good approximation. If you study physics, you'll see that. All right, enough for this. A point estimate is derived from a sample. Remember, a point estimator is used to find the point estimate, okay, or point estimates. A point estimator is the formula. Point estimator is the formula. You can think of it that way. Is the formula that is used to find the point estimate or point estimates. Okay, so let's keep moving. Confidence interval, we just talked about it, but let's go ahead and talk about it a bit more while we're on the topic. Confidence interval is an interval that you create from sample. Based off of your sample, you create an interval of this form, okay? Of this form, and you associate with it a level of confidence, which is a percentage. Like, remember the way I told you, you took a sample of 100 students and you found that on the average, they spend about 17 hours per week studying, all right? On the average, they spend about 17 hours per week studying. So based off of these, somehow you came up with it could be as low as 16 or as high as 18. So this is your confidence interval. And with this interval, you associate a percentage. It is called confidence level, okay? Now, there is a little bit of debate in the statistics community where they say, oh yeah, don't say that there is a 90% chance that this interval will include the true population average, okay? So there is a little bit of clarification. I'll clarify when time comes. But for now, kind of sort of in a vague way, you can assume that, okay, 90% of the times, probably it will include the true population parameter, whereas 10% of the times it will not. So once again, to summarize, you create a confidence interval or an interval of the form this, open interval, it has to be an open interval of the form A and B based off of your sample. And you call it a confidence interval and you associate a confidence level with it, all right? That's what it is. Now, how do you do the actual calculation? We'll get to the details of it. And well, I guess I'm on the actual calculation. So for the actual calculation, what we are using is really central limit theorem, okay? At the heart of all these things is nothing but the central limit theorem. Now, we have done the central limit theorem for, by the way, mean, for population mean. Remember, our conclusion of central limit theorem was mu sub x bar is equal to mu. And number 2, sigma sub x bar is equal to sigma over square root of n, given that n is greater than or equal to 30. This central limit theorem, actually, these conclusions are for mean, population mean, and population standard deviation. However, here the confidence interval we are talking about is P for proportion. Remember PMS? PMS, proportion, mean, standard deviation. For mean, we already have the formula, okay, the central limit theorem defined. As it turns out that for population proportion, there is a version of central limit theorem. And you technically don't have to go into that detail, but I think I mentioned it somewhere here. Okay. Here, mu sub p hat is equal to p. Remember, we had mu sub x bar is equal to mu last time, all right? So in this case, we use another symbol. Mu sub p hat is equal to mu. That means mean of the proportions, okay? Mean of the proportions, I mean mean of the sample proportions is gonna be equal to mean of the population proportion. And you know, I think this number is 10, and let me clarify, that's a typo. The NP must be greater than or equal to 10, not probably, it is 10, all right? So change that number. NP is greater than or equal to 10, n times 1 minus p, which is also known as q sometimes. Q is 1 minus p. So NP is greater than or equal to 10, and NQ, Q is 1 minus p, is greater than or equal to 10. If these two conditions are satisfied, then this will hold true, okay? Mu sub p hat is gonna be mu, and sigma sub p hat, standard deviation of the sample proportions, okay, is gonna be square root of p times 1 minus p divided by n. Square root of p times 1 minus p divided by n. It's like you can compare it side by side. This one goes with this one, right? And this one goes with the other one. Similar, sigma sub x bar is equal to sigma over square root of n. And I kind of wanted to bring this to your attention. So this goes with this, and this goes with this, the second one. This is the central limit theorem for population proportion. This is the central limit theorem for population mean, okay? For population standard deviation, we really do not use central limit theorem so much. We use something called chi-square distribution, and we'll talk about it. I think I'll have enough time to talk about it. By the way, it is not required by the syllabus or the contents that I'm supposed to cover in this class. I don't need to cover the standard deviation, but I want to. So we will be probably talking about chi-square distribution. We are making good progress in terms of time and everything. So we will go ahead and cover that probably. So Z is equal to P hat minus P. Z is equal to P hat minus P divided by square root of P times 1 minus P over N. That has approximately normal distribution. That has normal distribution with mean of 0 and standard deviation of 1. Now, this topics here is a bit advanced, by the way. It is a bit more mathematical. I just put it here and briefly went over this. Please make sure that you spend a little bit of time on this. And if you get too confused, don't stress too much, but remember these two conditions. And P must be greater than or equal to 10, and times Q, or 1 minus P, must be greater than or equal to 10. And if you just remember that the equivalent formula for proportion is mu sub P hat is equal to P, and equivalent proportion standard deviation is sigma sub P hat is equal to square root of P times 1 minus P divided by N. If you remember these two things, I'd be happy. Okay? And then from this, once we know the behavior, once we know, that's why central limit theorem is so central or important to the study of statistics. Once we can convert things to standard, normal distribution. So this central limit theorem ensures that this is normal distributed. Once we know that, we can kind of convert it into standard normal distribution, which is something we already know. All right. So once you know that a distribution is bell-shaped, it becomes significantly easier to study the properties of that distribution. But on the other hand, if we don't, then it becomes a bit more challenging. Okay, so let's see. Now, how do you find the confidence interval? And this page, again, maybe I should talk about it. I go through a bunch of mathematical derivations, and don't worry about it so much. We are going to find confidence interval using this formula. P hat plus or minus E, okay? P hat plus or minus E. E is called the margin of error. E is equal to actually Z sub alpha over 2 times square root of P hat times 1 minus P hat, all of it divided by N, okay? And that is the formula that I'm going to be using. And you should remember this formula. And using this formula, we are going to find the confidence interval. Now, this may, I promise that we were over the hurdle, the most difficult part of the course, but looks like you might find this a bit more difficult, but it is not really. I promise you, it is not as difficult as it looks. All of these mathematical derivations, don't worry about it too much. I'm gonna go ahead and just use the formula. The reason I'm gonna do it is that it's not the theory that is so much important, it's rather the application of the concept that is more important. Okay, it is rather the application. So I'll give you a little bit of theory, which I did already, how you derive, how kind of you convert the central limit theorem for population. While we talked about the central limit theorem for mean, I meant to say proportion. We talked about the central limit theorem for population mean, but we have converted it into the central limit theorem for population proportion, okay? And that is an important concept. And then using that, we can come to this conclusion, and you can read it up a little bit if you want. But I'm not gonna go over this because that will scare you off. We are gonna use this formula to calculate confidence interval. P hat is the sample mean proportion, which is just easy, X over N. I'll do problems in the next class. And Z sub alpha over 2, that's your kind of, you can think of it as a boundary for being wrong. We'll talk about it as well. And once you have P hat, and then you have everything. And alpha comes from confidence level, we'll have to derive, okay? So it's gonna be something that we will need. So there is a certain level of confidence, okay, with the confidence interval that you created, and alpha is associated with somehow with this one, and we'll talk about it. And now do not get overwhelmed. We will be talking about the examples in the next class, okay? I'll just do all of these examples, and I'll do so many of them that you will get feel for it slowly. If you want to get a head start, I'd recommend that look at this example, okay? Take a little bit of time and look at these examples, okay? And once you have a good sense of these examples, good feel for these examples, then it will start to come together how to calculate the confidence interval and make some conclusions or predictions. Not predictions, more like conclusions. All right, that's all for today. Any question, anybody? Everybody? Anybody, any questions?
No.
Everyone okay? All right. Thank you so very much, folks. You have a wonderful weekend and rest of the week. I will assign some new homework online. If you have time, please look at it. I will be covering those homework next time. All right. Okay. Thank you very much.
Bye.